today's video, we'll be discussing the last of the heat transfer mechanisms, and that is the radiative heat transfer, or sometimes we call this the radiation. Now, when we say radiation, I already know that you have been quite familiar with this term. Now, this radiative heat transfer doesn't require any medium, unlike conduction, which usually employs solids, and this convection, which usually employs liquids and gases. So radiation can happen whenever there's this EM waves, that's the electromagnetic waves, traveling through space. Now, there are just two basic equations that we need to understand before we proceed with the computation for radiative heat transfer. The first one is that the wavelength is equal to the speed of light divided by the frequency. So you can see there the units for the wavelength, the speed of light, and then this frequency. So the speed of light is given by 3 times 10 to the 8 on an estimate. And if you'll be pressing your calculator, that's around constant number 28. So you can just press it and then you'll be finding the exact speed of light. Now we also have this equation that is, you're already quite familiar with this, the famous Einstein's equation, the E equals mc squared, or that is also equal to the Planck's constant times the frequency. So the Planck's constant, which is 6.6261 times 10 to the negative 4 joule-second, that is constant number 6 in your calculator. And these two equations, they give us an idea that light is a wave and a particle. In this case, it's a wave because it has something like a wavelength, and it is also particle since, for example, we have a photon mass, and then this mass would give us the energy through momentum, or something like the movement of these molecules through propagation. So that's why light can be said to be a particle and a wave. Now, if we would look at the EM spectrum, so this is the EM spectrum, and as you can see, the light we can see, the visible light, is around 400 nanometers to 700 nanometers. So beyond that and below those wavelength, we can no longer see them in our in our naked eye. So, but we know that they exist because, for example, you can hear the radio broadcaster, you can hear the phone, or something like you can send messages or files through Bluetooth. So these waves exist in a way that we can't see them, but they're actually there. And to give you some idea of how this radiation works, it's just that if the wavelength is high, meaning the wavelength is very long, around, let's say, 100 meter, so these wavelengths are actually very low in energy. So as the wavelength increases, the energy decreases. They're like inversely proportional. That's why when you have something like the gamma waves, they exist only when you're in contact with those materials that emit gamma rays, or let's say X-rays. And if you're quite far from those materials, then you won't get exposed with the radiation. So here's the last picture here is a brief exemplification of our radiation. So when we have the alpha waves, and that's the weakest of all these alpha beta gamma waves, so it cannot pass through a paper. But for beta waves, it can pass through a paper, but it will not be able to pass on these perspex. So perspex is some kind of solid plastic, but it is a transparent one. So gamma rays will be passing through the two of this, and then some part of it would pass through this lead sheet. So that's how it goes for this electromagnetic spectrum. The idea is just the visible light is just around this wavelength, and as the energy increases, the wavelength decreases. So now let's talk about this Stefan Boltzmann Law. And this is one of the the most used law that you will be utilizing in this discussion. So the Stefan Boltzmann Law states that if the total energy or radiant energy emitted from a surface, it is proportional to the absolute temperature to the fourth power. So if we have something like the emissive power of a black body, that is E sub B, that is equal to the sigma notation here, and then times T raised to the fourth. And then this sigma notation here, that's the small sigma, it gives us the constant value of the Stefan Boltzmann constant, that is 5.6704 times 10 to the negative 8 watts per meter square Kelvin to the fourth. And if you would press your calculator, your Casio 91ES and the 570ES, you have there this constant number 31. So I'm actually adding some constant here, just so you wanted to like if you don't want to memorize this constant, then I'm allowing you to use these constant numbers from the calculator. So this is the equation expressed in the emissive power per unit area. So if you would translate that to our Q, then it will be like Q over A. That's why it becomes like this. And these two are the proponents of that law. This one is Joseph Stefan, and this one is Ludwig Boltzmann. So let's move on with the properties of radiation. For us to generalize and to give an idea on how we can approach problems, it is a necessity for us to understand how radiation works. And to do this, let's have the properties first. Now, when we imagine an incident ray, this one is the incident ray, being something like a straight line. So this incident ray, upon meeting or striking through a surface, we call this the surface of the material. So let's have here something like surface. So part of the incident ray will be reflected. So this is what we call the reflected ray. And then some of it will be absorbed by the material. And so some of them will be absorbed by the material and the rest would be transmitted. So apparently not all materials can, transmit this incident ray. Now I would like to give some notations that will help us in understanding this easier. So if we would represent the reflected ray as rho, and then this transmitted ray would be the tau, and then this absorbed material being the alpha. So by the nature of something like not a material balance, but if we would something like balance the fraction of the rays here, we could see that if we add the reflected ray with the absorbed ray and then the transmitted rays, then this fraction would of course equal to 1, since they are all the fractions from the incident ray. So this is one of the properties of radiation. So if you have the reflected ray, or the reflectivity plus the absorptivity plus the transmittivity, that should equal to 1. In a way that if you have something like the incident ray here, that would equal to all of the rays that we have here. And when we talk about reflectivity, we actually have two types of reflectivity. When we have something like a ray here, and then for example this is our symmetry, and then it reflects back in a way that the incident ray, this one, let's call it incident ray, and then this incident angle, or angle of incidence. So if it is equal to the angle of reflectivity, then we could say that this is what we call the specular reflectivity. So when we talk about this specular reflectivity, it means that when an incident ray hits a surface, it will not scatter the rays. So instead, it will just something like mirror the angle of incidence, and then that's where the reflected ray will go. Now, if we have something like a rough surface, so imagine this is the symmetry, then this incident ray will be reflected somewhere that is not at the angle of our incidence. So in such a way, in this case, we have something like the incident angle is not equal to the reflected angle. So we call this the diffuse reflectivity. So having this diffuse reflectivity, it gives us an idea that the surface that is stricken by this, the incident ray, that surface should probably be not smooth or rough. So that's how it goes for the properties of radiation. So the first one is that the absorptivity plus the reflectivity and then transmittivity is equal to 1. So if we have here the transmittivity is equal to 0 because some material doesn't transmit rays. So we could also say that the reflectivity plus the absorptivity is equal to 1. And in a way that if we want to express absorptivity, that is just equal to 1 minus the reflectivity. And then going back to this reflectivity, we have two types, the specular and then the diffused. So when it is diffused, the material is rough, so the incident ray would not reflect its rays in a way that if you mirror the angle, it would have the same value for the incidence angle. So that's all for our properties, and let's talk about this black body. Now, a black body is actually an ideal body, so it doesn't really exist. It is something that absorbs all incident radiation, thus doesn't reflect any. So if you can think of an object that would absorb all these rays, we could say that that's a black body. Well, assuming that all of the rays will be, of course, absorbed. And not all black bodies are actually black. So this means that if you, let's say, have some a material that looks black, it doesn't mean that it is already a black body. So the condition that it must satisfy is that this material should absorb all the incident radiation. So if it does, then it is still considered a black body. For example, snow is not black, but it is considered a black body since it absorbs all radiation. Now that we've talked about black body, let's try to give an example of how this black body works in a way that we can solve equations through the idea of a black body. So imagine this material, which is not a black body, is enclosed in this large enclosure, which is we would assume that this one is the black body here. Now if we have something like a material here, and we know that this enclosure has already dissipated heat through this material, we could say that the emissive power of this material here is equal to the heat flux of the surrounding or the enclosure times the absorptivity of the material here. And what if we try to substitute a black body through this with the same size, same area, same dimension? So at equilibrium, we could say that the emissive power of this black body would still be the same for such case. But we know that the absorptivity of a black body is actually equal to 1. So if alpha is equal to 1, then we could say that EB is equal to simply Q over A. This means that the emissive power of this black body would have absorbed all the heat that is being expelled by this enclosure. And if we would like to relate that on our material here, we could say that E is actually equal to EB, or the emissive power of the black body, times the alpha, which is the absorptivity. And with that, if we could take the absorptivity, that will be equal to E over EB. And that is the emissive power of the material over the emissive power of the black body. And this is now what we call the emissivity. So in this case, in this experiment, we could tell that when we have absorptivity in relation to a black body, that is still equal to its emissivity. And emissivity, we will be using that in our future calculations. Now this relationship here where alpha is equal to the emissivity, that is known as the Kirchhoff's identity. The emissivities and absorptivities that have been discussed are the total properties of the particular material, and they represent the integrated behavior of the material over all wavelengths. So real substances emit less radiation than ideal black surfaces, and the emissivities in reality of materials varies depending on the temperature and the wavelength of the radiation. So we have now actually three properties of radiation. So the first one is that this one we have the reflectivity, absorptivity, and transmittivity would equal to 1, and that if we would take the Kirchhoff's identity, we could say that the absorptivity is equal to emissivity. So with that, let's talk about gray body. If we have black body, that is, the absorptivity would be equal to 1. That is, it just takes all the wavelength, the radiation, and then it absorbs it. So that's why it's equal to 1. Now, if we would imagine this gray body is something like it deviates from the normal behavior of Kirchhoff's identity in a way that this monochromatic emissivity is independent of wavelength. So the substances with emissivities less than 1 would always be independent of the wavelength, and this is true to almost all materials, and we could actually tell or say that all the materials are, gray body, since they have actually emissivities that are less than 1. Even human body is 1, for example. And in this case, this is our general equation for gray body, that is Q is equal to the area and then the emissivity, which is independent of wavelength. That's why we can actually lump this up to some temperatures and it doesn't change. That's the essence of having this gray body. And then we have this Stefan Boltzmann constant, and then actually this should be t to the fourth and not t sub 4. Let me just edit here. I think I have copied this, and then the formula here is not raised to the fourth. Yes. Okay. So the gray body, it has something to do with this emissivity. That's why it's like from the equation that we have before, from the Stefan Boltzmann equation, we just have to plug in and multiply this with this emissivity, and now we're done with the new equation. Now let's talk about how we could solve this radiation in a way that we would employ all the applications that it has. So there are just three types of radiation that can be solved through some problems. So the first one is when the radiation happens to a small object from surroundings. So for example, a material is exposed to the environment, so it doesn't have any enclosure, doesn't have any something like material that is close to it. It's just resting on, let's say, on a road. A material is right there resting on a road. So this radiation that we'll experience by this small object from the surroundings, we'll be using this equation, okay, this one. And of course, we'll understand that when we try to solve for one of them. And then we have this radiation with convection and conduction, and this one is a really easy problem to identify, because when the problem has something like flowing liquid or water is forced inside the pipe, then there will always be this radiation, convection and conduction, and usually radiation will just be added just to complete this setting. So let's draw some pipe here probably, and so we have some radiation and then convection and then conduction. So that's the second one. And then the third one, which would be, well, I would say that radiation is a pretty straightforward problem. When we solve it, it's just like you're using this an equation here, you just something like modify it a little and then you're done. But when it comes to this radiation with shape factors, that's when it becomes really complicated. Radiation is easy, but when it comes to those problems that involve shape factors, it really is, it's not easy. And well, it depends on the problem, but when there are cases when you need to find this shape factor. Now, shape factors, or we can also call this the view factors. Let's have our view factors. This is a dimensionless property of a material, wherein if we have something like an object here, and then it has an area, and then an object here, so it has an area too. It is something like what this object sees from this A2, and then we would account all the radiation that will be sent by this A1 to A2. So if it's something like it emitted a fraction of radiation, then what could be the amount of that radiation that is absorbed or intercepted by this A2? So that's how view factor works. It's something like you have two materials, and then you try to evaluate all the rays that come out from that material, and then try to give the relationship between these two. So that's how view factors work. And these view factors can be solved by inspection, reciprocity law, and enclosure law. So let's have these view factors by inspection first. So as what this trick here says, it's inspection. So sometimes view factors can be solved by simply inspection. So for example, I have material, let's say I have a flat plate here, and then I would like to enclose that to a certain dome. So it is now already enclosed in a dome, and then let's have something like area 1 here and then area 2. So the area 1 is this flat plate and the area 2 is the dome. So it can be said that they have different areas. It can be designated they have A1 and A2 because probably they have different temperatures. So anyway, so if we would look at area 1, we could say that any incident ray or reflected ray, any ray that you can draw here by taking some kind of differential area here, it would something like view area 2, meaning it will all be intercepted by area 2. So we could say that F1, 2, meaning the ray or the radiation that is emitted by area 1 would be intercepted by the area 2, and that is equal to 1. So by inspection, we could say that all of the radiation that is emitted by area 1 would be intercepted by area 2. But how about if we talk about this area 2 with area 1? Now, this area 2 is actually a concave material. So if we would like to draw some radiation here or rays, you could see that for some reason it would strike its own surface. And with that, we cannot actually give the exact value here by just inspection. So we know that it's not 1, but of course it's not 0. So when does these view factors start to have some 0 value? And by the way, when we talk about enclosure, this one is an enclosure, imagine if you have an object, let's say you have something like 3 object here, and then you try to like enclose them in a certain material, so that's an enclosure, and this one is another example. So when you have an enclosure and then you have this surface, we have 2 surfaces, the number of combinations of the view factors would be equal to the number of surfaces squared. So in this case, the number of view factors would be equal to 4. That's why we have 1, 2, 2, 1, and then the other one would be 1, 1, and 2, 2. So that's all the 4 view factors that we can get. And when we talk about this F11, that means that we're trying to like find the view factors in between the area 1 and the area 1. So that's true. That's how the surface or this plane sees itself. And can you imagine if you would can you actually see yourself if you're just a flat plate? So that's impossible because all the rays are actually going out from this with angle that is less than, you know, pi over 2. So with that, the F11 should be equal to 0 simply because it cannot, you know, it cannot see itself. But F22, when we talk about this F22, we could simply say that this concave material would see itself. So it's not actually 0. It's not 0, but it's not also 1. Now we can also write this in a form of something like matrix, so that you won't be finding it difficult to like memorize what happens. So we can write it in a way like this so that you won't miss anything when you write it all. And remember, if you have something like this matrix F11 and F12, so it should be equal to 1, and then this F21 plus F22 which be equal to 1. So let me delete it first. So this F11 plus F12, which is just in one row, that will be equal to 1, and then F21 plus F22, they're just in one row, so that is equal to 1. And by this method, we're actually doing what we call the view factors by enclosure law. So it says here that if you have materials that are inside of a certain enclosure, all the view factors would be equal to 1. So if, for example, I have area 1, area 2, and then area 3, and then area 4 for the enclosure, so I could say that F12 plus F13 plus F14 and of course F11 would be equal to 1. So that is the enclosure law. And to give you a general property, we could say that the summation of all the view factors of ij given j is equal to 1 to the n would give us a value that is equal to 1. So given that this j is equal to 1, and then it is raised to, it goes higher depending on the number of surfaces that are existing inside an enclosure. So we're talking about an enclosure here. So if it's not an enclosure, let's say this example, this is not an enclosure since it's open to the surroundings. So this law is not applicable. You can find this enclosure law at your Paris handbook at 5-113b. So that's the equation for the enclosure law. Now let's talk about the last one, which is the view factors by reciprocity. Again, I would like to emphasize that this inspection could be something like Fij is equal to 0 or Fij is equal to 1. We usually solve for those in a way that we can actually see it. So that's how it goes for inspections. Now, when we talk about this reciprocity law, we could something like think of two objects, and then, for example, these two objects are block bodies, and then when we need to find the energy leaving surface 1 arriving at surface 2, we could say that this is the emissive power of this block body 1, So this is 1 and this is 2. And then its area, and then of course the view factor. So if we would be in equilibrium wherein there is no net change of energy and T1 is equal to T2, you could say that that is equal to the emissive power of the black body 2, and then that's the area 2, and then the view factor of 2 to 1. So now if the emissive powers of these two bodies are the same, then we could just cancel this out, and we could say that when we have an area and then this is equal to area 2 and then this F21, we could say that this is the reciprocity relationship, wherein if we have an area and then this view factor from 1 to 2, or from the radiation leaving at the surface 1 to surface 2, and then this area 2, and then the radiation leaving from surface 2 intercepted by 1, we could say that these two are equal by reciprocity relationship. So when you're given with A1 and A2 and then just this F12, you could actually compute for F21. So that completes the radiation with shape factors. We have the inspection, where we could just look at the incident rays and try to imagine an eye on that plane, let's say surface. So if you couldn't see yourself at that region, then that will be 0. But if you can see all of the other object, then that will be 1. Reciprocity law states that if you have two areas and then you have these view factors for each, we could actually equate them. And then finally, when there's an enclosure, the total surfaces, the fraction of, the view factors of each of the surface to the other surface would be equal to 1. So that's how it goes for our properties of radiation. And remember, if we have a net value here, so we equated this because that is equal to 0, the Q net. But if it is not, then the heat that is experienced by from 1 to, that's the material. So we could say that that is the area 1, and then the view factor, radiation emitted by 1, intercepted by 2, and then you have the emissive power of the black bodies. So this is how it goes for the equation. And then we can substitute actually this emissive power into something like the emissivities, and then the temperature, and of course the Stefan Boltzmann constant. So we could say that Q12 would be equal to A sub 1, and then F12, the sigma or Stefan Boltzmann constant, and then T1 to the 4th minus T2 to the 4th. So this is one of the equations that we'll be using as we proceed with the discussions and all the problem solving that is involved in this radiation. So I hope you understood how this quick derivation works. It's just that any material that is not exposed to the surrounding, meaning it has something like up in its proximity, there's another material that is the size is not actually very large compared to that material. We would always be using something like this shape factors. But if the material is simply it is just exposed to the surrounding, doesn't have anyone or anything that is in close contact with its area of in consideration, so we could say that that area or that small object is actually is experiencing a radiation from the surroundings. But when the material is actually exposed, or it has something like an enclosure, we should always be using these shape factors, and the shape factors would be determined depending on the three of this, based on the inspection reciprocity law and then the enclosure law. Now, this is not restricted to just 3 options on how you can solve for the view factors. Actually, there are a lot. Now, to name one, so one of the methods to solve for the view factors is just for contour integration. So contour integration happens when you need to find the view factor, and in general the view factor of a certain material is equal to the 1 over the area 1, because we started with 1, and then we take the double contour integral of these, let's say area 2 and then area 1, then multiply it with the cosine theta 1 and then cosine theta 2 divided by pi r squared, and then dA 1 over dA, dA 1 dA 2. So this is the general form of any view factor that we can solve, and it only gives us an idea that when you have an area that is exposed to a certain area of relative proximity, you can actually take the differential area of that and then do some double integration by contour integration, and then you can solve for the view factor. So what happens is that this r is actually the distance in between those two materials. So for example, I have a material that is something like this, irregularly shaped, and then this one is another one. So we have area 1 here. If I take something like a portion here, I can call that dA1, and then a portion here again would be the dA2. And if I would take the distance between, actually that should be a straight distance, so this distance here, and then I would take the normal vector out here and then the normal vector somewhere here. So I can take the theta here, and that would be the cosine theta 1, and I can also take the theta 2 here, and that would be the cosine 2, and then this one, the distance in between them would be the r. So this is how it goes for such kind of case where we would like to take the contour integration. When we talk about contour integration, if you're not familiar with this is an integral wherein if we have something like let's say this is a xy plane. So when you have something like this figure that is closed, if you would take the contour integral of this, then you're actually taking the integral of the shape, of this closed figure. So that's why it is called the contour integral. And when we're dealing with geometries and shapes, that's what we'll be using to find f12. But remember, this solution using this is a very rigorous mathematics, so we may not be able to finish all the discussion in just 1 hour if we would be deriving all of this. So the good thing about it is that the Paris handbook gave you already the differentiated or the integrated. So the good thing about this is that the Paris handbook already gave you the integrated equations from this contour integration. But of course, not all the geometries have been given. So let's check on the Paris for now, and let's read some of its golden data here. So I'm actually at chapter 5, and this is the natural convection, so you can read all about this. And remember, since we'll be using some emissivities, these are the table of emissivities. You can see here the emissivities and then all the temperature range. So you might be thinking about this. For example, the emissivities of these copper, something like this, is 0.028 to 0.031, and that's not actually changing a lot given the temperature here has already changed a lot. So when materials actually change due to temperature differences, then we could say that they are actually selective materials. Now these selective materials are those of the kind wherein these emissivities are actually dependent on the wavelength. So actually you can see them here, but usually they are employed to the industry just to modify things, probably those for paints and stuff that need to have these wavelength modified. So these are the emissivities, and for the first one we have something like this one, the conservation relations. This is actually the 8th edition, but it's located also on your 9th. So this one is this is what I've been talking about. This is the general direct exchange area, and this is their symbol for not F1, not F12 but S1 Sj. This is how they represent it. So it's actually a contour integral of double integral. Okay, so we have that one, and then you also have this reciprocity relationship. So you can see here it's the summation, and that should be equal to 1. Now we do have a lot of equations here. This one is the perpendicular rectangles. You can use this equation and also these parallel rectangles. And now we also have this radiation between parallel planes directly opposed. So this is the table, the graph. We also have the center to center distance tube diameter, and we also have the cross string method. So when we use cross string method, it's something like when you have an infinitely parallel material, you can actually draw 6 strings, and then you can assign all of the strings. You just do like the top and then the width, and then make the diagonal. And then when you do it using this formula, you can actually find the view factor. We also have the Yamato principle. We can also use this Yamato principle given by this equation. Where's that? Now this Yamato principle can be also used when evaluating the view factors. And the last one would be this radiative exchange in enclosures, or the zone method, which is the very mathematically inclined derivation. And as you can see here, you're using the matrix, all the inverses and all the dot product that you can get. So this is how it goes when you have something like total exchange area. You can also have this where's that, for transparent medium, as well as all of this. But the most important of this is not this description here. They're just representation of all the vectors that they have. That's why it's in bold. So the most important probably here are these, the final S1, S2. I'm sorry. So this S1, S2 is actually those that are very important, because this is what the view factors are. This is the view factor for two-zone enclosure. So for any two-zone enclosure, you can use this. And for those that are in a planar surface completely surrounded by the second surface, you can use this one, and you can see it from here by reading it from case 1 to case 4, all the stuff that you need when a plane A is exposed to a certain enclosure. You also have these parallel plates that are infinite, and then there's this case 3. And I would also like to discuss all about this F. So remember, let's try to solve the view factor for each. So remember, since I told you before, the number of the surface would squared for any enclosure would equal to the number of the view factors. So if we try to find the view factors here, so we could say that there are just 2 surfaces, and 2 squared would give us 4. So that's why there are 4 view factors here, and it is written in a matrix form. So this is F11, this is F12, F21, and then F22. So F11, it means that the area 1, we need to find the view factor of area 1 itself. So you cannot see yourself actually, so that is 0. But if it's F12, when 1 can emit all the radiation and it will be intercepted by 2. So in fact, this enclosure would take it also. That's 1. But of course, when it is 1, but of course, if it's F21 and F22, we couldn't tell that, for instance, how it really works. But when we use reciprocity, let's try using reciprocity here. We could see that when we take something like area 2, and then that should be something like 2, 1, that will be equal to area 1 and then F12. So in this case, if this is F11, this is F12, so this is our F21 and this one is F22. So if we take F12 here, that is equal to 1, so we could just say that A2 times F21 would be equal to A1 times 1. So therefore, F21 is actually equal to A1 over A2. That's why this F2 F2 here, this F2 is actually equal to A sub 1 over A sub 2. So that's the reason why it becomes A sub 1 over A sub 2. And using the rule that if we add one row, if you add this row, that will be equal to 1. That's why when we try to add this, that would equate to 1. And the same thing goes for here. So since it is an infinite parallel plate, so it is, logical to have this 0, 1, 1, 0. And it goes the same way for case 3 and case 4. So that's how it goes for such cases, and you'll be using that in a future computation. So you can read all about this, and you could see here there's another 3 zone. Because we used to have like 2 zone, we also have this 3 zone, and this is the general expression for that. Okay, so that's just for the discussion, and it will be easier for you to understand when we try to solve problems for this. So let's get into it. Now, to understand radiation better, let's try solving some problems. Now in this case, there is a triangular plate exposed to air. Now if you'll be reading this problem, just the first sentence, you might think that this could probably be convection. But remember, if the problem doesn't define or it doesn't give you what the exact. But remember, if the problem doesn't give you the specific heat transfer mechanism that you need to find, usually you would try to find all of them. The 3 of them. So in this case, the problem specifically asks for the radiation heat loss per meter of the base. So we'll be finding the Q of radiation instead of, probably adding some convection here. So it's just the radiation alone. Now to start with, the emissive power of a black body is given by the relationship of the Stefan Boltzmann Law, which expresses the Stefan Boltzmann constant and then T raised to a certain power, which is to the 4th. Now, this changes to Q over A when we try to give the heat in terms of heat flux, and then this becomes Q is equal to A and then sigma T to the 4th. And this is applicable if our emissivity is equal to 1, that is the ratio of the emissive power of the material to the black body. So if it's black body, then this E would be equal to 1. But if it's not, then Q would be equal to E and then A sigma T to the 4th. And in this case, this is how it works for gray bodies. Now, in cases where there is a difference in temperature, remember our Q net or Q12, it usually is equal to the area 1 and then the emissivity of at the first, let's just write the sigma notation first for the constant first, and then we know that this emissivity would be dependent on the temperature, so we could say that that will be something like E1 and then E2 for the second temperature. So this is how it works for the emissivity 1 is not equal to the emissivity number 2 for the different temperatures. But if the problem gives you, or it doesn't give you the difference in the emissivities, or there's just one emissivity, you could actually lump that up into 1, knowing that it doesn't change with the temperature gradient that is in the problem. So you can use this or this one. Now in the problem, as you read, we can see here that we're given just one emissivity, and with that we can actually think that this is constant along the temperatures of 20 and 85. So to solve for this, we have the radiation that is equal to area and then the Stefan Boltzmann constant and then the emissivity and then the temperatures raised to the 4th power. So we can substitute this, the area of a triangle, so we can imagine this triangle being exposed to the surrounding and nothing else. So the surrounding is very huge and the area would be very huge for the outside, but since this is just naturally exposed to the environment, we could think of this triangular plate being a small object. So in that case, the area of the triangular plate would be 1/2 base times height, because that's a triangle, so that's base, and then the height would be 12 centimeter. So we convert this to meters. And then we have the Stefan Boltzmann constant, that is about 5.6704. You can always use that constant number 31 for your calculator. And then we have the emissivity, which is unitless. The emissivity here is 0.75. And then we multiply that with the expression of the temperatures raised to 4. So I'll be deleting some of these, and then we can have more space. And then we have T1. So T1 is the higher temperature, so we have 85. And then we need to convert that to Kelvin. So it's not like the one we used to conduction before, because before we used to like we don't convert that because it's just a difference. But in this case, since it has to be raised to the 4th power, then we need to like convert this to the temperature that we need, so the 4th. Okay, and then so this will give us a value of 23.1397 watts, and because we don't have any base, so that will be watts per meter, and this should be over the base. So this is the answer for the first problem, where we have to find the heat loss of radiation per meter of the base of the triangular plate.